So this week is all about choosing the prior. And the choice of prior is going to depend in large part on the likelihood function. So what this video is going to go over, it's going to go over the idea that the likelihood function reflects the process that gave rise to the data. That's a very important concept. And I'm going to do that through some examples. And I'm going to begin with looking at some distributions that might serve as likelihood functions and explain how those different distributions reflect different processes that gave rise to the data. So we'll begin with the binomial distribution. And the question might be, what proportion of the population is right-handed? So the data would be binary. Individuals would either be right-handed, we'll deem that a success, left-handed, a failure, and let's say we assume we get Y successes, Y right-handed people in a sample of size n. What's the process that we assume that gave rise to those data? What we're assuming is that the number of successes in n independent trials arose as a random draw from a binomial distribution with this formula that has this parameter theta that reflects the probability of any individual being right-handed. And so our goal is to obtain the probability distribution of theta. Another example would be the multinomial distribution. So perhaps we're interested in what proportion of the population favors one of the 5 different federal political parties in Canada. Now we're dealing with categorical data. Now, in a sense, when we're back up here with the binary data, that's also categorical, but it's a special case of categorical in that there's only 2 possible categories. Now we've got 5 different possible categories. We sample n individuals, and the values of 1 to 5 are the number of individuals favoring each of the 5 different political parties. The process that gave rise to these data, what we're going to assume is number of individuals favoring those different parties, and individuals were sampled, arose as a random draw from a multinomial distribution that has this formula and parameters theta 1 to theta 5, the proportion of individuals in the population favoring each one of those parties. The Poisson distribution. The Poisson distribution example would be, we've got a kilogram of soil, and what we're wondering is how many colony-forming units per gram of some particular bacteria are present in that soil. So, what are the data? Well, we're going to have counts, Y, of colony-forming units from a 1 gram sample. So we're going to take a 1 gram sample and get those counts. So we're dealing with counts, and the data are going to include all possible values of integers going from 0 to infinity. So what's the process that gave rise to those data? The assumption is Y, the count observed in a 1 gram sample, arose as a random draw from a Poisson distribution that has that formula, and this parameter lambda that represents the average value of colony-forming units per gram in that big blob of soil that we began with. And our goal is to obtain the probability distribution of lambda, which is the average number of colony-forming units in our 1 kilogram blob of soil. And then we've got the normal distribution. So perhaps we're interested in the average height of females, undergrads in the Faculty of Ailes. So we measure the heights of n females, and the data consists potentially of all real numbers from minus infinity to infinity. The process. Each one of those heights assumed to have arisen from a random draw from a normal distribution that has this formula and 2 parameters, mu, which is the mean of the distribution, sigma, the standard deviation. And what we're going to be interested in is the probability distribution primarily of the mean, but also potentially of the standard deviation. So those are just some different distributions associated with different likelihoods, associated with different processes that gave rise to the data. Now, to further hammer home this idea that the likelihood function represents the process that gave rise to the data, I'm going to go over some more examples, how this might work in practice. So one thing about our likelihood function is that it should reflect how we think the world actually is. So in week 1, we looked at the idea of females versus not females in academic department X. Now, this probably isn't the best way to think about that because it actually conflates gender and sex, but it's probably an improvement over what we would have done 30 years ago when we had male versus female. But in any event, we're dealing with binary data, so the appropriate likelihood function would be the binomial distribution. But if you look at Government of Canada passport applications, here you can specify gender as male, female, or X. So if you were to describe the distribution for that, or the data for that, the data would be categorical and we'd be dealing with a multinomial distribution. Another example is that we plan our experiment, we get our likelihood function, we need to collect our data that's consistent with the process that's implied by that likelihood function. So let's say we want to determine the proportion of the population that's right-handed and we sample 30 individuals. We can't get lazy. We can't go out there and say, okay, I'm just going to select 12 different families and obtain 30 samples total from those 12 different families. And the reason for that is the binomial distribution assumes that the observations are independent. And because there could be a genetic component to handedness, individuals from the same family may not be independent with respect to whether they are right-handed or left-handed. And then a third thing we have to think about is that what happens, we plan our experiment, we have a particular likelihood function in mind, a particular probability distribution in mind, but then we discover that our data are inconsistent with that distribution. Well, then what do we do? Well, here's some examples. Let's assume that we're going to use a Poisson distribution, and a Poisson distribution has a single parameter, lambda, which is both the mean and the variance. So the Poisson distribution assumes that the mean and the variance are equal. We may look at our data and discover that, in fact, the variance is greater than the mean. If that's the case, we may no longer be able to use the Poisson distribution. We may elect to use the negative binomial distribution instead. Another example would be, we plan to collect some data. We're going to assume that the distribution is normal. But then when we look at our data, we find that it is right skewed and positive. What do we do in a situation like that? Well, we may want to consider doing a logarithmic transformation. That will work, but effectively what it does is it assumes our data are arising from a log normal distribution. So our likelihood function is no longer going to be normal, it's going to be log normal, and perhaps more importantly, it's going to change the interpretation of the coefficients. Now, this changing the interpretation of the coefficients is a very important thing. It's not particularly relevant to this seminar on Bayesian statistics, but if you are going to do logarithmic transformations, you might want to look at this thing in supplementary materials on eclass. So, bottom line, this week is all about the prior. The likelihood function is going to play an important role in determining the prior, and the likelihood function reflects the process that gave rise to the data.